Today we're going to learn about deriving the formula for the length of a curve in calculus. So let's say we had a curve like this. Let's say we just had this random curve and we had point A and point B. Now, how do we find the distance between these curves? Or not the distance, but how do we find the length of the arc between these curves, or between these points? Well, if we go back to one thing that we learned in the differentiation part of calculus, we remember that there was something like linear approximation, called linear approximation or Newton's method. So this is where we drew a tangent line to that point, and then we estimated where this point was. We also learned how to estimate the distance along that line from one point to the other point. So let's say we had from point A to point B a bunch of little other points in between that we knew. So what could we do then? So as you can see here, we have 4 different points. So this is the first case where we had just 2 points and one linear approximation, so we can see that it's a little bit off. But if we had another case where we had point A and point B, we know that one line would be way off if we just drew a tangent line to point A. And if we drew a tangent line to point B, that would also be way off. So let's say we also had 3 other points in between. So point 1, point 2, point 3. So now we have a total of 5 points. So what could we do there? Well, here's where we could do linear approximation at point A and find point 1, do a linear approximation at point 1 and find point 2, and same for 3 and B. So how does this happen? We're just finding points, right? Well, we remember that slope equals rise over run. So that means that we can calculate, that's the wrong thing that we're looking for. So if we find that point, we know that the distance formula says that d, the distance, is equal to the square root of x1 minus x2. So like just this value of x minus the a value of x. So x1 minus x2 squared plus y1 minus y2. So here's where their slope formula comes back into place that I was talking about earlier. So we know that slope is equal to rise over run. So we know that run will always be dx and rise will always be dy. So you can rewrite it as this, dy. Dy. Or, sorry, not dy, delta y over delta x. And we know that the slope, when we do linear approximation, will have to be f prime of x. F prime of x. So that means that delta y, which is the last part of the distance formula, x1 minus x2, which is also known as delta y, so that means that delta y would be equal to f prime of x times delta x. So we get plus f prime of x times delta x. So now what do we do? Well, here we can write so now what do we do? So here we get the distance between just 2 points. How do we get the distance between all the points, but separate each point, or between point A and point B, but separate them into 4 smaller intervals? How do we do that? Well, here's where we use summation notation. So we say that we have delta x, which is, so the length of the curve, so first just take this all in mind because I'm going to erase it now. So we have the sum from some point, let's say C is equal to 1, C is equal to 1, to some point n, or some value n, and we have a function, the square root of, now instead of x we're going to use n, or c, sorry, so c1 minus c2 squared, which is just delta c. So we have delta c plus f prime of x. This should be delta x down here, I'm sorry. Plus f prime of x, delta x. And as we know, these will both be squared. And it's delta c squared. So how does this help? Well, this helps because we know that this would be equal to the sum from c equals 1, which is our first interval, to interval n of the distance, or yes, the distance for c, so just delta c, the change in the x value for c. So delta c squared plus f prime of x squared times delta c squared. So how do we solve this? This doesn't look like anything we've done. Well, as you can see, we can distribute out, or take out, a delta c squared. So we get that this would be equal to delta c squared. This would be equal to delta c squared times 1 plus, and then we had f prime of x. F prime of x squared. So what would this be equal to? Well, as you can see, we're multiplying these two, so we can break apart this radical into two different radicals, one which is delta c squared and one which is 1 plus f prime of x squared. And if we break it apart like that, then we get that this will be just delta c, because the square root of delta c squared is delta c. So we would get this is delta c, and we have the square root of 1 plus f prime of x squared. So what does this look like? Well, this looks like a Riemann sum, right? So in a Riemann sum we have delta x, in this case it's delta c, and then we have our function f of x. So couldn't we just make this into the Riemann sum of, but instead of having f of x we would have this function here? Well, that's right. So a Riemann sum can also be expressed as an integral from a to b. So we have the integral from a to b of just this function, which is the square root of 1 plus f prime of x squared. So the answer to this problem is the integral from a to b and dx. So the answer to this problem is the integral from a to b of the square root of 1 plus f prime of x squared dx. And let me write this properly, dx. Today we learned about deriving the formula for the length of a curve. Thank you for watching this video.